Okay, so I'm going to continue on with starting at objective 2. So that's under SCR triggering circuits. So an SCR needs a pulse of current to trigger the gate when it's forward biased. Again, that's the two things that we talked about that it has to have before it conducts. The exact timing and speed required to provide repetitive consistent firing cannot be accomplished manually. So when we talked about firing or gating the SCR, they talked about a push button just doing that, but we can't physically have a push button that we can push fast enough to gate it in certain scenarios. So we use an RC time delay circuit to trigger it and provide phase control. The resistor and capacitor from a capacitor charging RC time circuit. That's these guys right here. So here's the capacitor here and the adjustable resistor. So remember we talked about capacitors, it was the T is equal to R times C. That's how long it takes the capacitor to build to a full charge. So if we can manipulate the value of R, we can change the time in how long it takes to build up to a charge. Okay, so the equation to determine the capacitor charge rate is T is equal to R times C. The value of R1 is chosen to give only a few degrees of phase shift when R2 is adjusted to 0 ohms. And the maximum value of R2 is selected so that together with R1, the amount of phase shift produced is close to 90 as possible. Okay, so we're using this R1 as part of the resistance too, but we're only adjusting the R2. So the capacitor voltage rises at a rate determined by the resistance of R2, the adjustable or the potentiometer resistor. By increasing the resistance of R2, it takes longer to reach the triggering voltage. This results in a larger firing angle and a smaller conduction angle of current through the load. Decreasing the resistance causes the capacitor to reach the trigger voltage faster and gate the SCR sooner, resulting in a smaller firing angle and a large conduction angle. So again, just what we talked about before, they're showing this discharge here once the capacitor is actually, or once the gate's been triggered, but it takes time to reach up to this voltage here. So it needs to reach the same voltage, but it's just going to do it longer if I increase the resistance in the RC circuit, in the timing circuit. So in this one, the firing angle is happening at 45 degrees. By increasing the R, it's going to take longer, and we can get up to a 90-degree firing angle. Well, a 45-degree firing angle gives me a larger conduction angle, so my load's going to see more voltage than with a 90-degree firing angle. So that's how we can adjust how much voltage is going to the load based on that RC timing circuit. The pulse trigger circuits for SCRs, another way of accomplishing the same timing control is illustrated below, where the SCRs are part of the rectifier and a pulse trigger circuit is used. Pulse trigger circuits control an SCR by providing current pulse of sufficient magnitude and duration to trigger the gate of the SCR, or thus turning it on. So the difference here is we were used to seeing 4 diodes. Again, we talked about this with that application for an SCR2. It's called a controlled bridge rectifier now that we have SCRs. So D1 and SCR2 are going to fire at the same time. This trigger circuit is going to tell SCR2 when to fire. With D1 conducting, it still takes SCR2 to conduct in order for the load to see voltage. So if we can control when the SCR2 is gated, we can control how much voltage is going to the load. And this trigger circuit is what accomplishes that for us. So the pulse of current is delivered from the primary of the pulse transformer. That provides a positive pulse to the gate of both SCRs, but since one SCR is forward biased at any time, it only turns one on. When L1 is positive, D1 is forward biased, and the current must flow back through to L2 through SCR2. In this alternation of supply, only SCR2 turns on because SCR1 is reverse biased. So then when L2 is positive, D2 is forward biased and SCR1 turns on when the gate pulse is triggered. So again, both of these guys are associated with a diode, and it's going to determine whether or not which ones are firing at what time. Even though they're getting pulsed at the same time, again, they're reverse biased in one part of the alternation, so we won't see voltage go through. So again, 2 diodes and 2 SCRs are required in the control bridge rectifier. The current rating needs to be only half of the load current. Since the SCRs are in parallel, they can be rated for 1/2 of the required load current. Okay, so that's just another way of doing it with an actual SCR as part of the rectification. Electrical isolation. Most circuits incorporating SCRs require electrical isolation between the low voltage controlling circuit, triggering circuit, and the higher voltage power circuit. A pulse transformer is usually used where isolation is needed. So the pulse transformer prevents high voltage from the SCR power circuit from affecting the low voltage components of the triggering circuit. The pulse transformer is built for transmitting a pulse of current from its primary to 1, 2, or 3 secondary windings. The core is non-ferrous or partially ferrous, which results in little inductive delay on the pulse from the primary to the secondary. The pulse transformer's primary receives a current pulse from the triggering circuit that feeds the gate of the SCR from its secondary. Okay, so again, it's just literally an isolation transformer, so there is no step on this. It's just protecting the components of the circuit from any spikes that may occur. Objective 3, smoke detectors. An SCR is often used as a switch that completes a low impedance path to the fire alarm control panel. They use photoelectric means to detect smoke or other proprietary means. The sensing circuitry of the smoke detector triggers the SCR into conduction, and it operates as a closed switch, completing a path for current to flow to the control panel. So this is forward biased, this SCR, all of these, this is a smoke detector. So what they're saying is they have either photoelectric means or another proprietary means of detecting that there is smoke around, and they will use that sensing circuitry to gate the SCR. Once it's gated, then it goes, the current going that normally goes through the resistor, which would give us a value of 10 to 13 milliamps, indicating a normal condition, because normally we're going through the underlying resistor and back to the panel. As soon as we trigger that SCR, now we have a path through the SCR back to the panel, which is going to result in a higher current than going through the underlying resistor. And that's going to tell us that there's an alarm. Once that happens, the panel would initiate the alarm sequence and start switch the polarity to the signals and bells, and they would start going off. If we have zero current, it just means that one of the wires broke, and it would go into a trouble condition at the panel. And we'll review all this when we talk about fire alarms too. Okay, but the SCR is there to actually help provide the initiating circuit, the path to initiate an alarm signal in the event of smoke in this case. So the next thing I talk about is triacs. A triac, again, is a member of the thyristor family of electronic devices, solid state switch that conducts in both directions and requires a gate trigger current like an SCR. Okay, so it will conduct in both, where we saw the SCR just doing it in one direction. The gate trigger current controls the turn on for both positive and negative cycles, again, allowing both through. Below is how triacs are represented in circuit drawings. The arrowheads show that it can conduct in both directions. So kind of see, it looks like an SCR, but with 2 arrows, and is basically showing that it can conduct in both directions, still having this gate connections, because we still need to trigger that gate in order for it to conduct. So the terminals are marked T1 for the main terminal, T2 for the main terminal 2, and G for the gate. The circuit below shows how the triac is connected relative to the load it controls and the control terminal connections for the gate triggering circuit. Again, here's T2, terminal 1, and then the gate connected to the triggering circuit. So we've got a VAC, an AC supply going to here, and we also have an AC output. A triac is equivalent to 2 SCRs connected in inverse parallel. SCR2 controls the load when T2 is positive with respect to T1. SCR1 controls the load when T1 is positive with respect to T2. So basically, regardless of what alternation we're in the cycle, we are going to conduct through, because we have basically 2 SCRs in parallel, inverse parallel, so the opposite direction, and their gates are connected together as well too. curve for the triac shows that it can be turned on in both directions. So we have current flow, again, once we're gated, whether we're in the, again, we were looking at this in regards to an SCR, it would be forward bias or reverse bias. It just was saying now that T2 is positive or T2 is negative, basically telling you that it's going to conduct when gated in both directions. Triggering preferences, a triac may fire with either polarity current on the gate. Although this provides reliable triggering and proper phase control, the triac should be connected as follows. So this is kind of a default that we'd use. Gate is positive when T2 is positive, and the gate is negative when T2 is negative. So we kind of want the gate polarity to follow T2's polarity. Okay, so if this is positive, this is positive. This is negative, this is negative. And again, just a rule of thumb that they stick to so that they're in the circuits the same all the time. Since the triac is used on AC circuits, it is commutated with class F or frequency commutation. The control circuit for a triac, phase control of triacs is accomplished by connecting a variable triggering circuit to the gate. At the instant the gate receives a current pulse, the triac is fired into conduction and load current flows for the remainder of that alternation of the supply. And then again will be commutated when it goes to 0. So again, we see our AC supply through here on waveform A, and then under waveform A, so we see we see that the firing angle in this circuit is at 60 degrees. Again, the firing angle and the conduction angle have to add up to 180 because that's the alternation. And then we see at a significant amount of this alternation going to the load. They'll say at the time that we're in our firing angle, the voltage exists across the triac, and that would be the same in an SCR2. The firing angle is basically when the voltage isn't going to the load, so it's basically sitting across the SCR or the triac until it's fired, then the voltage goes to the load. So then the load sees the voltage once we get into our conduction angle, and the triac is seeing nothing because it's going to the load now. Then we have the same firing angle happening on the negative alternation. Again, for the firing angle, the 60 degrees, we see that across the triac until it's fired. Then we see the rest of the alternation going to the load for the conduction angle. Now again, if we increase the firing angle, we're going to see less conduction, more voltage across the triac during this alternation, and less at the load. Again, it can be adjusted. You can see more or less voltage, so we have control still. But the important thing to notice is that we're seeing this load is seeing alternating current. A potential reduction of voltage from the supply, but still alternating. We're seeing positive and negative peaks on this. Okay, so that's different from, definitely different from our SCRs. The Diac trigger circuit. Triacs are generally controlled by Diacs, which are semiconductor devices, again, of the thyristor family. A Diac conducts when the voltage across it reaches the breakover voltage rating in either direction and does not require a gate. Okay, so the triac is here, it is requiring a gate, but the Diac is what's deciding what goes to that gate, and the Diac itself does not have a gate. Although they are available in a variety of breakover voltages, the typical rating is 30 volts, okay, for the Diac. The figure below shows the Diac connection with respect to the triac and the preferred instantaneous polarities and current directions that are used for triggering circuits. Again, we'd like to see this gate polarity the same as T2. So when T2 is positive, the gate is positive. When T2 is negative, the gate is negative. The triggering circuit pulses to the gate of the triac. They are positive or negative with respect to T1. To ensure consistent triggering of the triac, polarity of the gate should always be the same as T2. So some applications, again, it has to reach the 30 volts here in order to trigger the gate. So some applications for Diacs and Diac-controlled triacs would be lighting dimmers. So lighting dimmers for the first one. says the light circuit shown is phase controlled with the aid of an RC and Diac timing circuit. Dimmer switches use this circuit arrangement to control incandescent lights. So we still have our timing circuit, so our R1, R2, and our capacitor. Now we just have this Diac limiting the current that's going to go through it once it hits that 30 volts, okay? Again, on average, that 30 volts. So when the switch is closed, the circuit is energized with a voltage, again, from A to B. Components R1, R2, and C1 make up the timing circuit. So all these guys here. As the voltage rises above 0 volts after the 0 degrees, the capacitor C1 charges through the resistor in R1 and the light. When the voltage at D with respect to T1 is higher than the Diac's breakover voltage, the capacitor discharges to the gate, causing the triac to conduct. This drops out the voltage across the triac near to 0. With the triac voltage near 0, the load has the remainder of the source voltage across it for the rest of the alternation. If the resistance of R1 and R2 is low, the time to charge the capacitor is fast and the triac fires early. This results in a greater load voltage and the light becomes relatively bright due to a longer conduction angle. If the resistance is high, the time is slow and the triac fires later. The result is less voltage at the load and the light becomes relatively dim. So this circuit is typical for most commercial dimmer switches. The mechanical switch is mandatory for CSA, and the inductor limits the rate of rise of current and results in less noise in the circuit. Okay, so that's this inductor here. So again, we're using this circuit to decide how fast this capacitor charges, and then once it reaches the breakover voltage of the Diac, that's when it begins to trigger and conduct through the triac. Okay, so it's a combination of all these things that are going to decide when this is gated and when it starts conducting. The other example they give is for a shaded pole motor. These are in like in small motors used for hand tools or fans, that kind of thing. Other single-phase induction motors used for high torque have centrifugal switches and cannot be speed controlled, so these universal motors can be. If the AC is phase controlled to less than the rated RMS voltage, it causes the motor to run at reduced speed. This is accomplished with the use of a triac and Diac trigger circuit. The Diac does not conduct until it is 30 volts across it. This occurs at approximately 10 degrees of the sine wave applied voltage, which is usually 120 volt RMS, okay, or 170 volt peak. The triac is usually gate triggered with the Diac and the RC timing circuit for delaying the firing angle beyond 90 for slow operation. Okay, so they're basically, that'd be like a setting on your drill for fast, slow, or if you have 3 variable speeds. We're basically just moving the wiper on the R2. Again, it depends on the timing of this timing circuit here to when the breakover voltage is exceeded for the Diac and then triggering the gate for the triac. Okay, so again, same kind of theory applies, just a different application. Okay, so that's kind of the long and short of controlled rectifiers. I would say long more than short. We're going to do our lab and we'll help solidify these concepts as well.